I promise that I will do a little crash course or just quickly go through the chapter because lots of you were absent. So basically what I'm going to do is I'm going to go through the screens that we used in class and without interruptions and just quickly go through all the work that you need to know for this chapter. So we started by saying that we have protons and neutrons. You have that from last year or actually the year before already, that when we look at an atom, sorry, all my scribbles are here already from the lessons. So if we look at an atom, you know already that this is what it's going to kind of look like. I'm just going to put it there. So you have the nucleons. So everything that lives in the nucleus are the protons and the neutrons, and together they are called nucleons. All those particles in the nucleus. They make up the mass. You already learned this. They make up the mass of the atom. The outside, where the electrons are moving, so we call it an electron cloud. This electron cloud determines how large the atom is going to be, and we're going to look at that in a little bit more detail just now. Now, certain atoms are going to have the electrons will stop there, and then some of them will go bigger, and we're also going to look at that because of the different spaces that the electrons will occupy. So that you should have done already in previous years. Get rid of our huge atom. Then we spoke about cations and anions. It was also in your previous years. So we know that if it's an atom, then if it's got two protons in the nucleus, that means it's going to, in the outside orbitals, and you draw Bohr models already. If it's got two protons, which are positive, then you're going to have two electrons, which are negative. If I lose something that's negative, it means I've got more positives, so I'm going to end up with a positive ion, which would mean I've got a cation now. If I gain an electron, so I'm gaining something that's negative, I'm going to have an anion. I cannot move around the protons. It's only the electrons that I can move. So that you have done. Then isotopes was the next thing we looked at, and we said that's atoms of the same element with a different number of neutrons. So what that means is you will see on the periodic table they give you the mass of chlorine as 35.5. Now we can't have a half a proton. So what that means is if I take chlorine or any other element, and the one I used in class was neon, sorry, this is full of scribbles already, but you can see the idea. The one that we used in class is if I have neon, for neon to be neon, it has to have 10 protons. So you will see the small number stays 10. I actually told you after this that we like to write the nuclear notation with the mass number at the top. So we should actually have had the 10 at the bottom. Your periodic table, though, that you are using will have the mass number at the bottom. So it doesn't matter. Go and look at the small number. We'll give you the number of protons. So you can see the small number stays the same because that's the protons and that determines what element it is. But then if we look at the 20, 21, and 19, I can't just go and add them up and divide by 3 because nature isn't put together like that. You're going to have different percentages of each of these. So you need to have a weighted average. And we actually spoke about you being able to calculate your term marks like this as well. So if 90% of them has a mass number of 20, to get that portion, what this will contribute to the total mass, so we're going to work out this portion. We're just going to say that's 90 over 100, because I know that's 90%, times by 20, which is the mass. And then I'm going to do that for each portion. So here we only had 3%, so 3 over 100. And this is going to be 7%, so 7 over 100, we did there at the top, times by 21. When you add up all these portions, you will see that you end up with 20.04, and we already know that we can't have 0.04 of a proton or neutron, but it means that there are actually an average of that in our nucleus, and that is why we don't really have a unit in your books. If you want to add a unit, we can call it an atomic mass unit. So how many things are there that contributes to the mass, atomic mass units? But for now, don't worry about it. We're going to do it in grams later when we do calculations. That was just another example. This is also from last year. You know that these are the alkali metals, alkali earth metals. You know that the transition metals live here in the middle. You know that the non-metals are on this side of the periodic table and that the metals are on the other side of the periodic table. These ones here are called the halogens. These ones here are called the noble gases, and after this chapter, you will really know why they are called the noble gases. And then we've got these ones in between that you call the metalloids or the semi-metals already. You need to know these names still because we might refer to it. Remember, as I said, we want the mass number at the top, atomic number at the bottom. So it's always going to be big number at the top, small number at the bottom. Again, looking at isotopes, hydrogen can have three different isotopes. And I think I have a picture of them somewhere. Yeah, three different isotopes. So one with only one proton. So that means it will just be hydrogen 1 1. This one, it has to be hydrogen 1. So at the bottom, you must have a 1. But then this one has 2 nucleons. So there's going to be, the mass number is going to be 2. This one has 3 nucleons. So the mass number is going to be 3. So if you want to work out the number of neutrons, remember that you're just always going to say big number minus small number, give me the neutrons. You can say C. 3 minus 1 gives me 2. All right, and again, so this was just another example in your books. You could have worked out the relative atomic mass of europium, and you will see it's not actually the value that's on your periodic table, but that doesn't matter. It was just used as an example. All right, so the exercises I'm not going to do, you've all done that. Just again, the definition, very important. The isotope is an atom of the same element with a different number of neutrons, and that means they will have a different number of nucleons, and they will also have a different number of no, the mass number will be different, the nucleon number will be different, the neutron number will be different, but the protons will still be exactly the same. So we can ask you a question like this and say, what is the same? What is the different? What is different? But that we did in class. All right. Then this was just a random example that I did. Still more relative atomic mass example. So you can pause and try and do it and see if you get the same answer. This one was a little bit more tricky because we didn't tell you the percentages, but remember, together they must give you 100. So in this one, we said some is 30, some will be a mass of 35, some will be a mass of 37, and we wanted to know what each of them is going to be. So this is probably as hard as it's going to get because you know that if you've got a big sample of chlorine and the one part is X percent, then you know that the other part is going to be 100 minus X percent. So you know that already because together it must give you 100%. And that is why in the calculation, you will see that I used X there and I used 100 minus X there as my percentage over 100. And then all you have to do is solve for X. You do not need a fancy calculator to do it. You can do it with a normal calculator. If you get a negative answer, you must know you've done something wrong. It just means something went wrong with your algebra. Okay, then we looked at different ways that we can speak about or we can represent atoms. Bohr model you've already done in previous grades as well. And then we said, fine, now we're going to look a little bit further. So the Bohr model is just representing the big energy level that the electrons are living in. And for now, you in 288. And you will see that it's actually not as simple as that because electrons are negative. They don't want to be together. Remember, negative things repel other negative things. So I hope you have asked yourself the question before. Why would 8 electrons go and live in the same place? Like you should have done for the protons. So so Bohr's model works for a lot of things, but it doesn't always work. All right, so then we moved on from this and we said, fine, okay, this stuff you can just go and look at. So we also said that electrons can move up in energy level, which means they will be in an excited state. But now, where is my nice little picture? Okay, we will get to it now. But you will see, and you can go and look at this on PhET, the simulation. They have a nice diagrams of, and you can play around and build your own atoms. So in the first energy level, now remember in Bohr you had your positive nucleus with all your protons, and then you had your first energy level, and then you had your second energy level. But what happens there is the first one, this is just a little ball. So it's a spherical orbital, which is called an s orbital. But there's no space for anything else. So there can be two electrons there. Now, why can there be two? Is because the one will spin in the one direction and the other one will spin in the other direction. That's the only reason why they don't repel each other out of there. In the next orbital, this is also, please remember it's 3 dimensions, so that's a little ball again. So in this little one, so we call that the 1s orbital because it's in the first energy level and it's a sphere. The next one will be the 2s orbital because again, it's in the second energy level and it's a sphere. And the same as the first energy level, this one can only take two electrons, one spinning in the one direction and one spinning in the other direction. But now in that second energy level, I actually have a little bit more space. So I also have space for a p orbital. So there in that space, I can find two more electrons. So they can be two more electrons. Remember, always only two because otherwise they will start repelling each other. And there's going to be one like this. And then there's going to be one more difficult to draw, but it's going to come out of the page on this side and it's going to go into the page on that side. So I've tried to find a nice diagram for you. And as I say, there are lots of animations on the internet that you guys can go and look at. I showed my class this one, and it is there if you want to just go and play around with it. But you can see it's actually in 3 dimensions. So you've got a p orbital coming at you, you've got one in that direction, and you've got one in that direction. So you've got x, y, and z p orbitals. The names that you need to know for these people that have made these rules are the person that said that only two electrons can live in an orbital. So in this space, there could only be two electrons. He was Pauli. Pauli said that. And then Hund said that when I go into a p orbital, which I will show you now, that electrons would rather go and live on their own in an orbital. So first they will go, and if I do this, they will go one, one, and then one in the next one. And then once that is full, then they will start pairing up. Because remember, they don't really want to be together because they still repel each other. All right, then we looked at electron configuration. I actually did it with my class the other way around, and I started with the Aufbau because Aufbau leads to this very easily. But for electron configuration, now you're just going to say how many, just clean it all at once, how many electrons will be in every single, oops, that's not what I wanted to do. How many electrons will be in every single space? And we know there can only be two, but we know that in the first energy level, there can be only an s orbital. So that is why when we use the sp notation, we write 1 for first energy level, s for sphere. And then my first energy level is full. Then I'm going to go to my 2 energy level and I'm going to write S again because the first one is always going to be a little sphere, like a ball in 3 dimensions. And then I'm going to have not 3, it's still my second energy level, but now I'm going to have p orbitals and there are 3 of them. So you will have 2px, 2py in the y direction. So as you can see here, so it's x, y, and this one is z going into the page. So px, pu, x, py, and pz. So there are 3 different orbitals, but we combine them all in one. You can write them separately, we will mark it right, but we just combine them all and say, okay, there are 3 of them, so that means they can take 6 electrons. So when we do the sp notation or the electron configuration, we just say, okay, fine, 1s can take 2 electrons, 2s can take 2 electrons. 2p can take 3 electrons, and then you carry on until you filled up your element. So if you look at a specific element, I wonder what I've done with my periodic table. It is here somewhere here. If we look at a specific element, let's say we're looking at chlorine, I know that chlorine needs 17 electrons. So now, before you went to alpha, you didn't really look at how many energy levels to draw. So 2p, then we're going to go back to 3s, then 3p, And then we would go to 4s, but we're not, that's the last one. We don't go further than that at school. So now we already have 2, 4, 6, 7, 8, and that would be wrong for chlorine because I need to fit in 17. So I'm going to draw it for chlorine, 7. I should have the 17 at the bottom to be correct. So 17. So chlorine will have 2, 4, and then here we can go 6 because now there's 10 already. There's another 2, so it's 12. And then to get to 17, I need 5. And now you can see that that orbital those orbitals are actually not full. And that is when we started speaking about the valence electrons. So we said, fine, these electrons on the outside are called valence electrons because they are in the outside energy level. And these electrons here on the inside, they are called the core electrons. We spoke about that a lot. Now, if you are lazy, you will see, and that's also why I did Aufbau first, because then you can see it clearly. Now, you know already that everything wants to have a full electronic structure. So to get a full electronic structure, what chlorine must do is change this, because remember, if it's got 8, it's full. So what chlorine must do is get another electron. So if it does get another electron, it will become like the noble gas. And that is why all things react, because they want to get a full electronic structure. And that is where the shortcut comes in. So you look at the periodic table and you look at chlorine and you say, fine. Chlorine is going to be almost like neon. So you go to the noble gas that's just before in the periodic table. So I can say that is neon. Then after that, so this is the first energy level, second energy level. Then I'm in the third energy level. So after being neon, and that's why so that's abbreviated. We put neon there. That means it's got an electron structure like neon already. And then after that, we're going to have 3s and we're going to have 3p. In 3s, there's going to be 2, and 3p, there's going to be a 7. Oh, can't have 7. What am I doing? 2s, and it's going to have 5, sorry. And then that, neon has 10 already. So it's 10 plus the 7, and that is giving me my 17, which is what I wanted. Okay, so the reason why this is here is, okay, I'm going to actually talk about Aufbau first, and then I'll get back there. Where was my Aufbau? All right, so then I made you draw all the different elements, and I made you draw the Aufbau for all the different elements. And then what you saw from this is that every time when I'm in group 1, I'm going to have one valence electron. So hydrogen had 1. Then if we go underneath it, lithium also has 1. And everything in group 1 has 1 electron. Remember, when you do an Aufbau, remember to put this arrow here because it's the energy goes up as I go up. So the 1s will have the lowest energy. Then I'm going to 2s, then I'm going to 2p. And we did all of this in class, so you guys can practice that again. Now, if you look at carbon, I just spoke about a little bit. It's not really necessary. Where are these? Oh, they're not here. Okay, I'm going to have to do one of these for you. So if we look at our periodic table, let me find it again. Oh, I can't remember. See, my brain is leaving me. Let's take this periodic table from here. I'm just going to take that periodic table here to our Aufbau structures so that you can see how an Aufbau structure helps you so much. Okay, so there we go. So if I look at everything in group 1, anything in group 1, if I draw, so let's pick on the potassium, 19 electrons. So I'm going to go, now what you saw, so I'm just going to go to the summary. What you saw is that everything in group 1 will have 1 outside electron. So everything in group 2 will have 2 outside electrons. And what I mean by outside electrons is the ones in the outside energy level. So if I go 1s, 2s, 2p, 3s, 3p, 4s, and so on, there are D and F orbitals, but we don't really, we stop at 4s for school purposes. So if I draw it for magnesium, I need 12 electrons. So 1, 2, 3, 4. Then I follow, remember, in opposite spin, Pauli's rule. Then Hun said, one alone, one alone, one alone, and then they pair up, pair. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and magnesium needs 2. So now if you look at this energy level is full already, and it's going to look exactly like neon. Now you'll see why I said it's easy to do the alpha first, because that looks exactly like neon with 10 electrons. And then all I need after that is my 3s orbital that has 2 electrons. So that will be the alpha structure, and that will then be the condensed sp notation. But if you go and do the same thing for calcium, I'm just going to do it fast. So 1, 2, 3, 4, 5, 6, 7. Pauli, Hund, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And this brings me to 4s already. Now you can see that again, these energy levels are full. So the 1s and the one first energy level and the second energy level is full. So if you look at calcium, that's going to give us argon. So you're going to write argon, and then all you've got left after that is again 4s, 2. So now what I want you to see here, and we did it step by step for every single element, is that everything in group 2 will end up looking like this, where it has 2 um, electrons in the outside energy level that we call the valence electrons. So the valence electrons corresponds with the group number. So in group 1 it will have 1, in group 2 it will have 2, and now that is what I pointed out later. Group 3 is what we used to call group 3, is now group 13. So because of the transition metals behaving weirdly, we don't put them in our trend. So group 3, the old group 3 would have 3, but now because we're numbering these as well, it's going to be 13. So you will see you just have to minus 10 each time. So this is 3, 4, 5, 6, 7, 8. And these ones will then always end up with a full electronic structure. And that is why they are noble gases, because they don't need electrons, they don't want to give electrons away, they're happy the way they are, they don't want to mix with anyone. Lewis diagrams very, very, very important. So now we just take the outside electrons and we make a dot for each of them. So that is why for oxygen, I looked at in which group oxygen is, and I said oxygen is in group 16. So if you minus a 10, it's group 6. So it's going to have 6 valence electrons. Now remember, when we do the valence electrons, we're going to do 1, 1, 1, 1, so 4 of them, 5, 6. And now you can already see that there's a space and there's a space for electrons to come and bond later. The next chapter we do is all about bonding. So you're going to look at the group number, and that's going to tell you how many electrons to do. Then I just showed you the Lewis structures of everything. And I just added our periodic table because this is the one you get on your IEB sheet. And then here you'll see these ones are the ones that are numbered like our ones. Group 14 will have 4. Group 15 will have 5. But the old numbering system was like this, where we said 3, 4, 5. And it really doesn't matter. You just need to remember to take the 10 away. But each time that will tell you how many valence electrons it has, and then the period number will correspond with the energy level. So these will just be in the first energy level, so it will only have 1s. These ones will have 1s and 2s and 2p. These ones will have 1s and 2s, 2p, 3s, 3p. So it's because it's the third one. So you can have all of them there. I hope I'm not talking too fast. Exercise again, I'm not going to go through that. Then we looked at atomic radius. Now remember, we said it's the electron cloud that determines how big the atom is going to be. So that means here in energy level number 1, where I only have those few electrons, I'm actually just going to take my periodic table again with me. Energy level number one, I only have one energy level around my positive nucleus. So it's my positive nucleus and only one energy level. Now, as I go down in the periodic table, you know already that the next one will look like that, my nucleus again, but now that will have the s orbitals there, and the next one will have s and p orbitals. So as I go down, I'm adding an energy level each time. So that means as I go down, the atomic radius actually gets bigger and bigger and bigger because I'm adding an energy level each time. But if I go across a group, now if you look here, all of these will be in energy level number three. So if I go and draw them, so if I go to energy level number three, I know that they are going, so if you draw the S, you can draw SP, you can draw alpha, it doesn't really matter. Bohr still actually helps to draw that. It means I'm going to have three energy levels. And these electrons are all going to be in that same energy level. So I still have a positive nucleus. I then have my first energy level, which is already full because I'm in period number three. Then I'm going to have my second energy level, which is already full as well. So there I've got my two electrons. There I've got my next eight electrons. And then I go outside to my valence electrons. And now these electrons, because remember they are being pulled in by the nucleus that has a positive charge, and electrons are negative. And remember, positives and negatives attract, and you can even work out the force using your electrostatics on these things, because you know that a proton and an electron have the same charge. The one is just positive, and the other one is negative. So what you're going to do is you're going to say, fine, as I now have electrons building up, for sodium, I'm going to have one electron in the outside energy level. So there's only one electron moving around in that electron cloud. But for magnesium, I'm already going to have two. For aluminium, I'm going to have three, and so on. So I'm going to add more and more and more. So by the time I get to chlorine here, I'm going to have actually seven of them. I keep on saying seven. Yeah, it is seven. Seven electrons. There, it's not the p's only; it's the p's and the s's. So there you go. You've got your two and your s, and your five and your p. Okay, there we go. So that means that I've got a lot more electrons now. And remember, electrons repel each other. So that means that outside circle, because of the fact that there's more electrons, is oops, drawing the wrong way around. They are being pulled in by the nucleus, and the nucleus gets stronger and stronger. So they're the same. They just in that energy level. It's not getting bigger because I'm adding an energy level. What's happening is that this nucleus here, my nucleus is pulling with a force of 11. Here, my nucleus is pulling with a force of 12 protons. There, 13, 14, 15, 16, 17. So as I go across, my nucleus is getting stronger and stronger and stronger. So it's going to pull this electron cloud in and in and in. So as I go down, I said it's going to get bigger because each time I'm adding an energy level, adding an energy level, adding an energy level. But as I go across, because of the nucleus getting stronger and stronger and stronger, it's going to pull my electron cloud closer. And that is what I'm summarizing this diagram. And you can see as I go across, it's getting smaller and smaller and smaller. As I go down, it gets bigger. And then we just quickly spoke about the ions. If I remove an electron, remember now there's less electrons in that electron cloud. So that means less repulsion, and the electrons are going to be pulled in closer by that nucleus. Yeah, if I add an electron, there's going to be more repulsion, and that means my electron cloud is going to be bigger. So always when you form a positive ion, you're going to see that your size between your atom and your ion is going to decrease. You're going to have a smaller ion than atom. But if it's a negative one, it's always going to increase in size. All right, then we looked at ionization energy. And if you don't know what ionization energy is, you're not going to be able to do the questions on ionization energy. It's the energy needed to remove an electron from an atom. So that means I need to pull electrons away. Now, if the electrons are very close, and that is very important, if the electrons are very close to the positive nucleus, that means it's going to be very hard to remove them because that electron's being pulled by this nucleus. If that electron is far, far away, it's going to be pretty easy to remove that electron. So the close electron is going to be hard to remove, and the far electron is going to be easy to remove. Now remember, when we say first ionization energy, it means that that's the first electron that I'm going to remove from one atom. Second ionization energy would just be the second one. But now if I've removed one already, the nucleus this time stays the same, but I've removed an electron. Now it means this electron is going to be pulled in more because it's now part of less electrons, kind of. And then what it means is that it's going to take more energy to take that second electron away. And that's what we spoke about this table in a lot of this graph in a lot of detail. And that is why the general trend is, as I go across, because they're getting closer and closer to the nucleus, and the nucleus is getting stronger and stronger, it's going to be much harder to remove the electrons if you look at the periodic table, and therefore the ionization energy is going to increase from. So if you even look here, they're closer because the nucleus are getting stronger, so it's going to be harder to remove the electrons. So as I'm going from the left to the right, my ionization energy is going to increase. And you will see that the numbers here shows it's general, remember? It's a general trend, because then you will see that there's also little jumps. It goes 1, 2, 1, 2, 3, 1, 2, 3. So you know already in your alpha structure, we go S first and then we go P. So it's the 2s, for instance, and 2p. So when I'm looking at those electrons, the first two will be in the s orbital. There we go, 1, 2. Then it's going to be 1, 2, 3, 1, 2, 3. So now remember, ionization energy means I'm removing them. So it's kind of going in reverse. So to remove that one, I'm going to need a certain amount of energy. To remove the next one, I'm going to need more energy. So that's why it's 1, 2, 3 with a higher energy. And then one, oh, I drew this very badly. I'm not supposed to draw it like that, remember? You go 1, 1, 1, and then 1, 1, 1. I know we're not going to be able to see how you've done it, but if we only had 2 here and you end up with something that looks like that, we will take off a mark if you don't let them spin in one direction first and then the other direction. Okay, so I think you see it. So it's to s orbital, p, p. S orbital, p. So first 1, 1, 1, p. S orbital, 1, 1, 1, p. Okay, you can see the pattern there. We will not ask you ever to draw a graph like this. Your graphs are going to be either straight lines or curves. Please remember that. This is just to make conclusions from. And then we spoke a little bit more about that, and I referred to the periodic table. And here we just said, if someone asks about the nucleus and electrons needing to move inside into the nucleus, and we mix it with electrostatics a little bit there. All right, then determine the electronic configuration. This was just questions again, so I'm not going to actually speak about this anymore. You can go look at it. Electronegativity is now very, very, very important. So electronegativity is the is the tendency of an atom to pull in an electron. Ionization energy was the energy needed to remove an electron. Now we need to pull in an electron, and you will see that in your table, fluorine is the highest, because you can think about it. Fluorine only adds a positive nucleus and then one energy level, and then straight away those outside electrons that I'm removing is right there, and there's already 7 of them. Okay, I know I should draw them 1, 1 first. 7 of them. So that means very, very easily fluorine would take up another electron so that it can have a full electronic structure. So the tendency of fluorine to attract an electron is very high because it only needs one, and it's so close to the positive nucleus. So that's why it attracts it so easily. Chlorine is a little bit lower because now that electron still, it only needs one, but it's a little bit further away. So that means it's the attraction comes from a little bit further. So it's not going to be as strong of a pull than what fluorine was. Okay, we spoke about this in detail, but then not what we're going to do in the next chapter in a lot of detail is what you will then see is that some elements, when they are strong enough, if the difference is in electronegativity is very big. So the one we looked at is, for instance, if I look at fluorine here, that's 4, and I look at lithium here, that's 1, that difference is 3. So it's pretty big. And that means fluorine will take the electron all the way. So it will take the electron from lithium, and that means lithium will become a positive ion, fluorine will become a negative ion, and you know from electrostatics, a positive and a negative thing will attract each other. So you just keep on remembering that. So if it's transferred, we can have ionic bond, but then sometimes the difference is not big enough. And then it's not strong enough to steal the electron for itself. And then they're going to end up sharing electrons. But as I say, in the next chapter, we're going to look at bonding in a lot of detail. For now, you just need to know if the difference is very big, you're going to have an ionic bond. If the difference is small, you're going to have a covalent bond. And that, I think, brought us to the exam type questions. So that's where I'm